Welcome to this presentation about the background to Genelec Aural ID, or obtaining your personal head-related transfer function and using it in your work. When you want to monitor audio, you basically have two possibilities. You can be using loudspeakers for monitoring, or you can be using headphones. Let's first explore loudspeaker-based monitoring. When you use loudspeakers for monitoring, you have certain important benefits. You can always locate loudspeakers in the room, no matter where they are located, and no matter where you are located in the room. When you use two or more loudspeakers, you can create virtual sound images between the loudspeakers. In this way, loudspeaker monitoring enables you to hear the soundstage, and you can work with the virtual sound image locations and the impression of space that you want to create. In traditional two-channel stereo, your virtual sound images appear on the horizontal line between two loudspeakers. In immersive formats, three or more loudspeakers can create virtual images that are placed not only horizontally but also vertically where you need to have them. How does the headphone monitoring differ from this? Headphones cover your ears. This has important consequences, because headphones eliminate the acoustic effects of your external ear, your head and your upper torso. This removes your ability to hear direction of sound, or to localize sound. All sound seems to be happening inside your head. You lose most of your ability to hear the sound stage or space. Delivering accurate sound color can be challenging when using headphones, and the presentation of sound color may not be as accurate as it would be if you were using loudspeaker-based monitoring. Despite these challenges, headphones are very popular monitoring instruments because they have certain very important capabilities. First of all, headphones can deliver excellent dynamic range. This is useful in several tasks. For example, when you are checking your microphone line feeds for quality, or when you're checking editing issues, or when you're cleaning or splicing audio, and any other task where you can benefit from excellent dynamic range. The aim of this presentation is to study how we could enhance the use of headphones for monitoring. First, let's look at how we can localize sound. The traditional explanation of directional hearing is the duplex theory. Roughly, it works like this. We have two ears. These are located at some distance from each other. Therefore, we can have two effects. First of all, there can be a level difference between the ears, and this level difference can depend on the direction of arrival for audio. And there can be a time difference for the audio to arrive at both ears. The first one is called ILD and the second one is called ITD. ILD is created because of natural sound attenuation over distance. When the distance difference to two ears is different, this creates a level difference which the brain can detect and interpret as the direction of sound. This can work conveniently at high frequencies. At low frequencies, the wavelength of sound can be significantly longer than the dimension of the head, such that the level difference remains small. Then ITD can have more significance. Depending on the direction of the audio source, the sound can take longer to travel to one of the ears. Then brain can use this information to decode and understand the direction of audio signal. This is thought to be a significant mechanism at lower frequencies, where ILD cannot work. These two phenomena, ILD and ITD, are in the core of the duplex theory. The main criticism for duplex theory is that there can be several positions for audio sources that can produce the same ILD and ITD. For example, these two shown here. Yet, when you hear this kind of situation, normally you can easily tell the direction of the sound source. In addition to this, we know that when you are listening with only one ear, you can still tell the direction of sound. So we need more than just a duplex theory to explain directional hearing. The additional information that we use for localizing sound comes from the shape of the external ear, the head and upper torso. These shapes of our body reflect and diffract audio. These reflections and diffractions change with the direction of sound. The direct sound into our ears is accompanied by reflections and diffractions of your shoulders, chest, and the shapes of your external ear, and this combination of reflections and diffractions changes whenever the direction of arrival for audio changes. When we place microphones into our ears and measure the impulse responses from a sound source to both ears, we obtain the HRIR, or the head-related impulse response. In this example here, recorded with the sound source on the left side of the head, we can see that the left side impulse response is higher in magnitude. The right side impulse response is lower because the audio has to diffract around the head to reach the right ear. This level difference is related to ILD. In both impulse responses, we actually see a lot of fine structure, and this indicates that audio is arriving to each ear using many different diffractive pathways over a longer period of time. The location difference between the two peaks in the impulse responses is related to ITD. It is useful to look at the symmetry planes relative to the head. These planes are the horizontal plane at the ear height, the frontal plane dividing the front side to the back side at the ears, and the median plane dividing the left and right side front to back. Consider a sound source in the front. In the front, the ITD and ILD are the same. Also, the spectral effect of all the diffractions and reflections is the same for a person that has left-right symmetry. When the sound source moves on the horizontal plane at equal distance from the listening position, from front to back, directly at the side, there is a maximum value of ILD and ITD. The sound color effects by diffractive pathways are very different in this position. When we continue moving with the sound source to the back, again the ILD and ITD become the same. The coloration effects are not the same as when the source is in the front, but they are fairly similar. And in fact, sometimes people report of a front-to-back confusion when there is uncertainty about the audio source either being in the front or in the back. When the sound source moves across the frontal plane, the ILD and ITD initially are at maximum. When the sound source moves above the listener, both ILD and ITD are zero. When the sound source finally moves to the side, the ILD and ITD have again maximums, but the sign of this maximum has been reversed. The sound color effects of diffractions and reflections are continuously changing when the sound source moves on the frontal plane. The sound moving on the median plane is very interesting as a case. For any point on the median plane, the ILD and ITD always remain zero, yet we can easily understand the height of the sound source. This is an example of the importance of the specific diffractions and reflections in the external ear, head and upper body. As we all have slightly different shapes, these diffractions and reflections combine to a unique personal head-related impulse response, or HRIR. To understand what head-related impulse response contains, we can use the Fourier transform. When we take the Fourier transform of the head-related impulse response, we obtain what is called the head-related transfer function. The Fourier transform converts the impulse response data into a presentation that helps us understand about the magnitude of audio at different frequencies, as well as the phase and delay in audio at different frequencies to each ear. For example, for a sound source located directly to the left of the listener at 90 degrees azimuth angle, we see the level difference is modest at low frequencies but starts growing significantly above 2000 Hz and becomes significant. The distance between these curves is the inter-aural level difference, but you note that the difference is not constant but varies with frequency. Also, the shape of these curves depends on the individual. The phase information in head-related transfer function contains information about the time delay between the audio signal reaching the left ear and the right ear. For our direction of audio signal directly on the left-hand side, we see that the delay to the right ear is higher. This delay is the ITD, or the inter-aural time difference. We also see that the delay is not exactly constant but varies with frequency. How this variation happens is very personal to each individual. We can actually see that the combination of the external ear, the head shape, and upper torso details work as a filter for audio, and this filter has very specific properties for each person. The reason for this is that all the anatomic details for every one of us are slightly different, leading to differences in how sound is diffracted and reflected. Looking at a wide range of elevation on the median plane and azimuth angles on the horizontal plane, we can see that the magnitude response of this head-related directional filter mechanism is complex, and understanding about the personal anatomic differences, we know that the details of how this filter works likely are highly individual. The magnitude effect in the HRTF is shown here in two parts. On the left you see the magnitude effect that is common to all directions in the head-related transfer function. This is called the common transfer function, or CTF. On the right you see some examples of directional magnitude responses. For example, on the median plane at azimuth angle 0 and 180 degrees, the magnitude effects are very similar between the left and right ears. This should be expected, as we are on the symmetric location in the left-right direction. You can also see that the magnitude response between the 0 and 180 degrees directions do not look the same. This enables us to differentiate between the frontal sound and the rear side sound in reality. The explanation to the common factor can be understood by considering an object in the sound field. Close to the object, the pressure at certain frequencies goes up when the audio diffracts around the object. This is also familiar in early studies of the optimum loudspeaker cabinet shape, where diffractions are causing frequency-dependent magnitude changes and acoustic loading in this example of a spherical loudspeaker cabinet shape. When the head and torso of a person enter the sound field, similar diffraction happens. This causes a change in the sound level that becomes evident in the common transfer function. The head-related transfer function also enables us to extract information about ITD in all directions. Here the ITD is calculated using the phase information in the head-related transfer function. Although the ITD is not constant as a function of frequency, at the median plane the ITD tends to be close to 0. The ITD increases towards the locations to the side of the listener. Even if on the median plane the ITD is close to 0, please keep in mind that the magnitude response as a function of frequency is changing significantly when elevation changes. Then the sound color change works as the main cue for detecting the sound source height. Is it significant to obtain your personal HRTF? Well, first of all, several head and torso simulators with roughly human shape and microphones inserted into ears are on the market. However, they don't look the same. So the technology itself is slightly challenging here. It is easy to see that if the specific anatomic details are important in delivering the correctly working head-related transfer function, the differences between these alone indicate that substituting your own personal head-related transfer function with another set of head-related transfer functions obtained from a head and torso simulator may not work as you would expect. It's possible to obtain your personal HRTF by placing microphones into your ears and taking measurements from all directions you're going to need later. This can be done in an anechoic room. Such measurements are rather time-consuming and require significant skill. The alternative method is to use photogrammetry. Photogrammetry is a method that can find the surface shape that is related to a sequence of photographs taken of this surface. In our case, the surface is the person's external ears, upper body and torso. A sequence of images can be captured using a video, and this can then be processed to create a 3D computer model of a person. This model then can be used in simulating the pressure fields around the person, and in this way, head-related transfer function can be calculated in all necessary directions. Here is an example of an increased speed demonstration of how this kind of video can be captured. Using a standard mobile phone, a sequence of pictures is collected. The external ears are videoed in more detail to enhance accuracy. In addition to this, dimension photos are needed to scale the 3D computer model so that acoustic details appear at correct frequencies. The resulting 3D model of a person is detailed and contains the anatomic details that contribute to personal features in the HRTF. The external ear is modeled with very high accuracy. The Aural ID data contains 836 different directions for sound. Because the calculations are based on the complete specific 3D anatomy, the resulting head-related transfer function data is completely specific and personal in all directions. So, how can we use this personal head-related transfer function data? The traditional two-channel stereo arranges two audio sources at plus-minus 30 degrees on azimuth angle relative to the listener. Surround systems place up to 7 audio sources around the listener at the ear height. Immersive systems introduce more layers, typically one layer above the listener. When we want to get an accurate presentation of any one of these systems, we must create virtual sound sources at the directions where the loudspeakers should be. The head-related transfer functions for each ear and for all the necessary directions of audio are then applied to create all the left and right ear feeds for all the virtual sources. Once your personal head-related transfer function has been applied, you experience the correct direction of audio, correct color of audio and externalization, meaning that you get the sensation that the audio signals are coming from a loudspeaker and not inside your head. If we have the traditional channel-based audio system layout, the processing engine, for example, a plugin in a DAW, receives all the channels and generates a two-channel binaural composite feed for the headphone. The same principle applies to modern object-based audio formats where the metadata specifies the direction of audio. One word is necessary about headphones. Headphones do not have a flat frequency response, but typically a frequency response that models the human hearing in order to deliver a sensation of neutral sound character once the external ear and head shape have been eliminated. One such equalization is called the diffuse field equalization for headphones. When your personal head-related transfer function is used in processing audio, this headphone equalization should be compensated, so that the headphone is not changing what the head-related transfer function is doing for you. So finally, to conclude, we have been looking at the head-related transfer function, how you can obtain it, how it can be used in creating accurate and reliable monitoring of audio over headphones.